Hello, my name is Chris Fitzpatrick, and I did my second public lecture on origami, and I thought it was very interesting. I am currently minoring in Japanese, and I was looking at something that piqued my interest, and I found the public lecture on origami, and obviously Japanese origami basically go hand in hand. But I thought it would be very interesting to check it out, and I was correct. So some things that I learned that I didn't know were the behavior of objects, were that the behavior of objects depends on both composition and shape. Deformation affects Hooke's law. Kevlar and all bar towers take notes from origami. Origami folds can be categorized into either mountain or valley folds. Maekawa's theorem: if a vertex can be folded flat, the difference between the numbers of mountain and valley folds must be 2. And Kawasaki's theorem: a vertex is flat foldable if and only if we can alternatively add and subtract the angles between creases to get 0. A problem that is known as NP-hard in the STEM field is something that is easy to find physically, it's easy for humans to find, but very difficult to find by computer. Gaussian curvature is curvature in 3 dimensions. So if you have a cylinder, the Gaussian curvature is 0 because it is not, the curvature isn't positive or positive negative in 3 dimensions because one dimension has a curvature of 0. A sphere has a positive Gaussian curvature because the direction of the curvature is the same in both a Gaussian XY graph, and then a saddle has negative Gaussian curvature. Protein folding can be compared to origami, and kirigami, which is origami but with cutting, can affect the stretchability of paper, which I thought was very interesting. Some stuff I already knew is that origami is useful engineering. I knew Hooke's law, which is the force of a spring. A standard sheet of paper can be folded 8 times due to the exponential force caused by a paper fold, and origami patterns can be seen in nature. Some things that sparked my curiosity were the different effects of deforming objects and how that affects tension and force, the different uses of origami in engineering beyond compressing solar panels, the mathematical uses of origami beyond what they said in the lecture, and the similarities between really intricate origami folds and fractals, and the use of computers to create intricate origami designs. I thought all of those were pretty interesting. And some things that relate to my own area of study. I'm a computer engineering major, and so I kind of bridge the gap between computer science and electrical engineering. So I kind of look at both fields. And so the folding of solar panels for transport, that's partially in my field because I deal with the construction of electronic objects or electronics. Foldable phones for the same reason, and carbon sheets in relation to kirigami. And the carbon sheets is a bit different. That's more... that's still in double E, and certainly that can have electronics implemented into it, but it's not directly in the double E field. But yeah, and let's see. Unfortunately, I couldn't really follow up on the topic outside of the lecture because, once again, these are all online lectures. But besides that, I believe that I've gone over everything. Let's see. I am not rickrolling, I promise. Let's see, introduction, summary, what did they learn? Expand. Yeah. All right. Sorry that I just glossed over the rubric, but yeah, I believe I've gone over everything. I thought that was a really cool lecture. If you guys have a spare hour, obviously there's no public lecture review 3, but if you guys have a spare hour, or if you want to speed up the video and get through it quickly, you can certainly do that. I thought it was very interesting, and you might as well. Yeah, have a great night.